Hello, AP Physics. It's Steven Zawicki, your teacher. Once again, I wanted to help you understand some of the derivations for solving some problems in the textbook, since the textbook skips a couple of steps here and there and assumes that you know things that you might not know otherwise. So the first one I want to go over is the projectile landing and or launching and landing at the same height. So I've drawn a diagram to help us understand some of the basic bits that go into this problem. The first thing that we should remember is that at the apex, the vertical velocity switches from being positive to negative. And since it's switching, that means that the velocity at the apex, so I'm going to call this VYA, is 0 meters per second. Okay? At some point, it's got to pass through 0, and that is when the velocity changes from being positive to negative here. So if we want to find the time to the apex, which is helpful, we know that the velocity y at the apex is equal to the initial velocity in the y minus the acceleration of gravity times time. We can write this out in a little bit of a different way. We know that the velocity at the apex is 0. And we know that Vyi is on the opposite side of the angle, so we can use Vi sine of theta using our trigonometry here. And then that's going to be minus g times the time to that apex. So solving for time, we subtract Vi sine of theta onto the other side and then divide by negative g. So our two negatives cancel out and we get time to the apex equals Vi sine of theta divided by that acceleration of gravity. So now that we have this time to the apex, we can use it to find the total height that our projectile travels up to. So the first thing we're going to need is the equation for position in the vertical direction. So that's y final minus or equals y initial plus Vyi times time, and then it's minus because gravity is negative 1/2 the acceleration of gravity times time squared. So we know that the Vy final is just going to be the height, right? That's as high as it's going to go since we are using the time to the apex. The initial height is 0 because it starts on the ground. And then we know Vyi is Vi sine of theta. We can also plug in our time to the apex into time. So then it's going to be Vi sine of theta over the acceleration of gravity. And I'll use parentheses here to represent that those were different variables. And then we subtract 1/2 acceleration of gravity, and then we square that time again. Okay. So I'm going to work this out a little bit slower for you than they do. They just kind of do all of the steps in one to save some space. So here, our VIs, right? This full thing is now squared. So it's VI sine of theta. So sine of theta squared and VI is squared divided by the acceleration of gravity minus 1/2 g over Vi squared sine of theta squared divided by g squared. All right, so now we got some canceling going on. Our g's cancel. So we get Vi squared sine of theta squared divided by g minus Vi squared sine, oops, I forgot that over there, sine of theta squared divided by 2g. All right, so notice we have the exact same thing here, except for this 2. So I just have half of that value. So what I do when I subtract these two from one another, I end up with a positive half. So it's VI squared sine of theta squared divided by 2g. That is our equation for height. All right, so our last piece is to find the horizontal range of our projectile. So it's going to be launched and lands at the same elevation. So you'll notice up at the top that I have simply multiplied our time by 2 to get the total time. Often in this class, I will represent total time by T sub TOT for tot, or short for total, right? So we want our equation for position in the horizontal. So it's going to be x final equals xi plus the velocity initial in the x direction times t. Remember, there is no acceleration, right? Nothing is here because there's no acceleration in the x direction. Also notice at the top that I have represented vi of x, or sorry, that should be x sub I. I'll fix that. Is equal to vi cosine of theta. Remember, the horizontal component is on the opposite side, or sorry, on the adjacent side, so we're going to use cosine instead. So I can plug things in for these two pieces, right? I know my total time, right? I want to find the total range. I don't want to just find the range to the apex. I want to find the range for the total. And I need to substitute in for the x component. So I'm going to plug those in. So we get, and the initial position is 0, so I'm just going to get rid of it, right? This is gone. That goes away. So it is vi cosine of theta times 2 vi sine of theta over the acceleration of gravity. I could clean this up a little bit so that I can put things together, right? It should be 2 vi squared sine of theta cosine of theta all over the acceleration of gravity. Now this isn't very clean, but there is a trigonomic identity, and it mentions that this identity is on appendix B.4, and it is that sine of 2 theta is equal to 2 sine of theta cosine of theta. Notice we have all these pieces. We have the 2, we have the sine of theta, and we have the cosine of theta, so I can substitute this in, and it's going to make it a lot cleaner for us. So plugging that in, the final range is equal to vi squared sine of 2 theta divided by the acceleration of gravity. This is your full derivation for the range of a projectile landing or being launched and landed at the same elevation. Last little tidbit that I want you to know about, and it mentions it at the bottom, is that anything that is symmetrical about the 45-degree angle will have the same horizontal range. So if I have something that is at a total angle of 60, right, that's 15 above 45, then something that is 15 below at 30 will have the horizontal range. So the range at 30 degrees is going to equal the range at 60 degrees, and that's because of that sine of 2 theta. Since it's 2 theta, every time you have something that's going around that point, then it will be the same range. Something that is steeper, right, has a higher horizontal arc. So if I move these guys around, I'll move this over here. So if I have something that has a high horizontal arc, right? It's got a lot of time in the air because it's going up. It has a really high Vy component, but the Vx is much smaller, right? Now, if I change this around, so that the angle is much shallower, right? It can go far, and that's because it's got a large Vx, but it doesn't go up very high. It doesn't have very much time in the air. So even though it's going really fast in that horizontal direction, it doesn't have much time. So you're doing this trade-off, right? If you throw something with a constant or a consistent velocity, 25 meters per second, you can only trade off the y component and the x component, the vertical versus the horizontal. If you give it more horizontal component, then you're getting rid of time in the air. If you get rid of, or if you add more vertical component, right, you're giving more time in the air, but you're not allowing it to travel as far across. So this is the trade-off that you have.